So, good evening, everyone. Welcome to the week number 9 related to structure analysis course. So this is your problem solving session wherein we will try to solve the problems related to topics what you have covered in the current week. So, regarding the previous week, how we have summarized. So, the class was conducted yesterday as a compensatory class which was not held in the previous Saturday. So in that we have seen that how we can use method of consistent deformations in determining the unknown reactions, or you can say redundant forces and moments in the statically indeterminate trusses. So whether your truss is of first order indeterminacy or the second order determinacy, we have seen through the problems that how we can solve them using force method. So what we will do today, we will solve the problems related to beams that are expected to cover in the current week, and we will solve them using force method. So let me share my screen first, then we will see what kind of problems you are expected to solve in the current week. I hope the screen will be visible to everyone. So let's start this session. So this is your week number 9 for the problem solving session. So introducing myself, my name is Pranam Mahajan. I'm a PMRF scholar in Department of Civil Engineering from IIT Madras. So what we generally do in these sessions, we will try to solve the problems related to the topics what you have covered in the corresponding weeks. So till now, we have covered up to week number 8. And in this, we have seen how the problems can be solved related to trusses, beams, and frames for statically determinate structures, as well as when we have moving load over the structure, then how it will affect the behavior of the shear force and the bending moment diagram that we have seen using influence line diagram, wherein we have applied Mueller-Bridge law principle and we have seen how much maximum bending moment and shear force can be observed based upon the proportion of load that are moving over the structure. Later on, from the week number 7, we have introduced force as well as the stiffness method, which can also be corresponded as flexibility and the displacement method, wherein we have seen in case of indeterminate structures, how we will solve the problems and determine the unknown forces and moments that we call as redundants. So for that, in the previous week, we have seen in the trusses that we have utilized the method of consistent deformations, wherein we have used one compatibility equations. Using that, we have seen that how we can determine the unknown forces. So we have covered the problems for 1 degree indeterminacy as well as second order indeterminacy. So today we will solve some problems related to beams using force method. So describing about the force method, the algorithm will remain same what we have discussed in the previous lecture. So in this lecture, we will directly solve the problems regarding that, utilizing the same principles what we have covered in the previous week, or you can say yesterday, because that class we have conducted on yesterday. So topics covered in the week number 9, these are statically indeterminate structures, wherein we have solved we will solve the problems for beams, or you can say continuous beams, using force method. Now, looking about in the question, so the question is given to you. In this, you have a cantilever overhand beam subjected to a propped support at the middle of the section, and a clockwise moment is applied at the free end of the cantilever beam. So what the question is, let's understand first. So shown below is a statically indeterminate beam Now using unit load method, let the redundant be VB. That means your vertical reaction at B will be VB, and you can express this VB to be equal to H1 because we are interrelating the previous equation that we have covered in the last two questions of the previous week. Now you have to remove the effect of redundant force and obtain statically determinate beam, and then calculate the deflection at B of the primary structure. Okay, so this is the first step, or you can say second step after calculation of static indeterminacy. So if in this case we have to calculate static indeterminacy, so your static indeterminacy, if I write here, your static indeterminacy in case of beams, how you will describe it, that will be equal to number of reactions number minus number of available equations, or I can write E. So in this case, your total number of reactions are 3 plus 1, 4, and number of available equations, that are 3 equilibrium equations, and from this you will get the degree of static indeterminacy to be equal to 1. Okay, that means you have to remove one redundant force to make the structure as a determinate, and then solve the problem as a primary structure. Fine. So let's make this structure first as a determinate structure. So how we will do that? So we will remove the support reaction at B to make the structure to be determinate. Fine. So let's remove that first. So let's say this is your cantilever beam. Okay. So after removing your prop support, you will be left with only one moment at the free end, and your total length of the beam, if I write it, would be L. So this is your total length to be L. Now we will draw the bending moment diagram for this structure. Okay, so its bending moment diagram will look like this. And its value will be M, and we are making it to be M upon EI diagram, so that will be M upon EI. Fine. So this is your M upon EI diagram. Now what we will do, we will determine the deflection at the support B. So let's mark, suppose if you have this support B at the center. Okay, so that means how you will determine the vertical displacement at B. So we will use moment area method. So let's write using moment area method, your vertical displacement at B will be equal to area of the bending moment diagram between A and B, and it's multiplied by the corresponding moment. Okay, so I will write here area of M upon EI diagram between A and B let's write this in the next page. Multiply by corresponding lever arm. Okay, so your vertical displacement at B, as referred previously, it would be suppose we are mentioning it to be delta B. So that will be equal to area of the bending moment diagram, that will be M upon EI into L by 2. And now it's lever arm, and lever arm will be L by 2 by 2, that will be equal to L by 4. That means your deflection at support B due to free moment at support C will be equal to ml square divided by 8 EI, and this will be in upward direction. Okay, now what will happen if we apply a unit displacement at the corresponding center? That means again we are considering the same length of the beam, and now in case of providing free moment, if we provide center unit load, or you can say central unit reaction, okay, then how the bending moment diagram will look like for this? Okay, so using unit load method, now we have to draw the bending moment diagram for this case. I am copying this diagram in the next page. If we try to make the diagram for this, how it will look like? So that will be linear and its value will come out as, so since this length is L by 2, so it will be equal to L upon 2 EI. Okay, so this is your M upon EI diagram for unit load. So let's say, suppose we have marked it to be negative. So this will become a positive because it is causing a sagging bending moment. Okay. So due to this, so vertical displacement, or you can say vertical deflection for unit load it will be equal to, let's say I am writing it to be FBB. It will be equal to PL cube upon 3EI. So here P is 1, multiply by L by 2 because length is L by 2, divided by 3EI, and that will give you L cube upon 24 EI. Okay. Now using the concept of compatibility equation. So using compatibility equation, you have delta B plus FBB into BY to be equal to 0. Delta B you have calculated to be equal to ml square upon 8EI plus your FBB, it came out as L cube, not square, L cube upon 24 EI into BY. Now solving this for BY, you will get BY to be equal to 8EI upon ML square into 24, sorry, this will be equal to minus ML square upon 8EI into 24 upon EI upon L cube. This will give you 3M upon L with a negative sign. So your BY come out as minus 3 upon L. Fine. So this is how you will calculate your unknown force in case of beams using force method. Okay. So I have covered the whole problem, but in this question it is only mentioned to you that you have to determine the deflection at B of the primary structure. So your deflection at B of the primary structure will come out only this delta B. So I will mark it here. So let's say this is your delta B. So this is the only solution for question number 1. Fine. Now I have completed the whole question and determined the unknown force. Let's say what other questions tells you. So your next question is, it is continuation of the previous question as I have completed this in a whole. So in this it is mentioned to you that refer to the figure of question number 1. In order to solve the beam using unit load method, we need to solve for x1, that is your unknown force. So here H1 I have mentioned to be equal to By. Fine. Where it is given to you the corresponding compatibility equation. Okay. And it is expected to calculate the flexibility coefficient F11. So this flexibility coefficient will be the displacement due to unit load that we have provided by removing the redundant force. So as calculated previously, so this FBB will become your flexibility matrix. Okay. So your F11 will be equal to FBB, and it will be equal to L cube upon 24 EI. Fine. Now, what is your next question? So this is also a continuation of the previous question. Now in this question, it is telling you to calculate the absolute value of H1 as mentioned in the previous question 1. So as we have seen here, H1, we mentioned it to be B1, By. Okay, and we have solved for By, and this By will be equal to minus 3 m upon L. So your Xy equal to By is equal to minus 3m upon L in downward direction. Fine. So this is your final answer related to indeterminate beams. Okay. So let's solve another problem. I think the next problem will be different one. Yeah. So now you have one uniformly variant load that is applied over a prop cantilever beam in which the end A is fixed support and your end B is having a prop support, or you can say a roller support. So let's read the question first. So in the question it is mentioned that shown below is a statically indeterminate beam. Solve using unit load method. Let the redundant be By. So here let By will be equal to H1. Now remove the redundant force By to obtain the statically determinate beam, that is your primary structure, and then calculate the vertical displacement at B, that is your dl1 of the primary structure, taking EI to be constant throughout the structure. So you have to perform the same procedure that you have considered in the previous question. So let's solve this first. So since it is not mentioned, but we will also see what will be the degree of static indeterminacy in this case. So your degree of static indeterminacy that is ds will be equal to R minus E. R is the number of unknown reaction. So in this case, it is 3 plus 1, 4 minus number of available equations. So in this case, your available equations are 3 equilibrium equations. That will give you indeterminacy of first order. Fine. Now after that, it is given to you that you have to remove the redundant force. Okay. You can see here that remove the redundant force By to obtain the statically determinate beam as a primary structure. So now let's remove this and then create the primary structure. So I am removing the support at B, and then we are applying the uniformly varying load over the beam. Now, after providing this uniformly varying load, your beam has become now statically determinate after removing of the roller support from the free end B. Okay. So let's say your load is W and your total length is L. Now we will again use the moment area method to determine the deflection at the free end. So let's draw the bending moment diagram for this case. So if we draw the bending moment diagram for this case, how it will look like, let's see this. So this will be like a second order parabola. I think this looks like an overlapping section. Yeah, now it's fine. So if I write here the maximum value, so since it is providing the hogging moment, so the value will be negative. So this is your negative, and your maximum value will be equal to load and its corresponding moment, that is 1 by 2 into W into L, that is the load, and it will be acting at a distance of L by 3. And since this is an M upon EI diagram, so 1 upon EI will also come into picture, and that will give you WL square upon 8 EI. So your maximum value here is WL square upon 6 EI. Sorry, not 8 EI, it is 6 EI. So this is your M upon EI diagram for uniformly varying load. Fine. Now how you will determine the deflection at end B? Okay. So in this case, you will take the moment of this diagram from point B. So as mentioned there, your deflection, let me write vertical deflection at end B DL1, as mentioned previously, it will be equal to area of this bending moment diagram multiply by lever arm with respect to B. Okay, so that means your DL1 will be equal to area of this bending moment diagram, that will be equal to 1 by 4 into WL square upon 6 EI multiply by 4L upon 5, that is your lever arm, and it will be equal to W L. I think I have missed one L. That is 1 by 4 into the total length will also be there. Let me write here. So that is L into 4L upon 5, that is your lever arm, and it will give you WL to the power 4 divided by 30 EI. Okay, so now this has become your deflection at the free end of the cantilever beam when it is subjected to uniformly varying load at the free end. So this is the deflection for the primary structure. Now let's see what other questions tells you, because now I am breaking down this question into step by step. Whatever that is mentioned, we will solve that, and finally we will combine it again. So your next question is a part of the previous question. In this, it is mentioned to you that in order to solve the beam using unit load method, you need to solve for H1, that is your unknown force in the equation, where dL1 is the vertical displacement that we have already calculated at the end B of the primary structure. Now he is telling you to calculate the flexibility coefficients of the beam as mentioned in the question number 4. So in order to determine the flexibility coefficient, we have to use the unit load method. Now what we will do, we will remove all the external forces and apply a unit load in place of the redundant force. So let's convert this whole beam into a unit load diagram. So using unit load method, okay, so let's draw the diagram for this. So that will become your cantilever beam with a unit load at end B. Fine. So this is your 1 unit. And this is your cantilever end. This is your end A, this is your end B, and your total length is L. Now what you need to do, you need to determine the flexibility coefficient. So how you will do that? You will apply the same moment area method and then determine first the M upon EI diagram for this structure, and then calculate the moment about the end B, and that will give you the deflection, or you can say flexibility coefficient for this unit load diagram. So let me copy this diagram in the next slide, and then we will try to solve it. Okay, so now you have this unit load diagram. So how its M upon EI diagram will look like. So let's see that. So if I try to make the M upon EI diagram for this case, so due to the concentrated load, it will be like this. Fine. And if you try to determine the value, it will come out as L upon EI. Okay, let me write it. M upon EI diagram. And I will write the maximum value to be equal to L upon EI. Okay. Now your F11 in this case will become area of M upon EI diagram multiply by your lever arm with respect to B. So that will be equal to 1 by 2 into L into L upon EI. That will give you area of the M upon EI diagram. Multiply by the lever arm with respect to B. That will be 2 upon 3 into L. Okay. So your final value for F11 will be equal to L cube upon 3 EI. Okay. And you can confirm this from your standard result also when you are having a point load at the free end. Okay. So in that case, what will happen? That you have the result to be equal to PL cube upon 3 EI. And when you have unit load, and it will become L cube upon 3 EI. Fine. Okay. So previously you have calculated it to be a negative bending moment. Now you have calculated it to be a positive bending moment. Okay. So let's solve and see what the next question tells you. Okay. So your next question tells you that in order to solve the beam using unit load method, we need to solve for H1, which is your unknown. That is the only condition left now in this equation. Okay. So in this torsion, the X1 is redundant given by Bi. So it is telling you what will be the value of the vertical reaction at the fixed end support and the roller support of the beam as mentioned in the question number 4. So first we will determine the reaction force By, and that will be equal to your X1 in this torsion. Okay, so let's use this equation. So using compatibility equation, that is DL1 plus F11 into H1 to be equal to 0. Now we have determined all the values in the previous two questions, that is your question number 4 and question number 5. So let's substitute that. So your DL1, as you have calculated previously, it came out as WL to the power 4 divided by 30 EI and plus you have L cube upon 3 EI into H1, which is your By. Okay, so if we solve for this, we will get H1 to be equal to minus WL to the power 4 divided by 30 EI multiply by 3 EI upon L cube. This will give you the value of H1 to be equal to minus WL upon 10. Fine. So this will become your reaction By. Okay. So I think if we take one of them to be negative, you will get the reaction to be a positive one because your DL1 came out to be the negative. This is your negative now. So this DL1 will be negative. And if you put it here, this will be negative. And now it will become positive and positive. Fine. So this is your vertical reaction By. Now to determine reaction at fixed support, how we will do that? We will use summation of vertical forces to be equal to 0. Let's say I will write it to be Ay. So your Ay plus By to be equal to your total force, that will be equal to 1 by 2 into W into L. By you have already calculated it as WL upon 10. Now from this, if you calculate Ay will come out as WL upon 2 minus WL upon 10. That will be equal to 8 upon 20. That is 4 upon 10. That will be 2 upon 5 WL. So that will be equal to 2 upon 5 WL. Fine. So now we have calculated both the reactions in the fixed support as well as in the roller support also. Okay. So this is how you will solve the problems related to beams which are indeterminate, okay, using force method. Now let's solve some more problems. Now your question number 9 is telling you you are having a continuous beam subjected to a 50 kilonewton load at the center of each span. And let's read the question first. It is mentioned that shown below is a statically indeterminate beam. Solve using unit load method. Let the redundant be By. Let By be equal to X1. Now remove the redundant force to obtain the statically determinate beam and then calculate the vertical displacement at joint B of the primary structure. So similar to question number 4 that we have done, we have to remove the redundant force and then solve them and determine the vertical displacement at the joint B. So first of all, we will determine the degree of static indeterminacy in this case. So your degree of static indeterminacy is equal to ds equal to r minus e. Your r here is 2 in the hinge support, 1 in the roller support, and 1 in the another roller support, minus 3, which is the total number of equilibrium equations. That will give you the value of ds to be equal to 1. Okay. Now what you have to do, you have to take this structure and remove the redundant force as mentioned in the question to be taken it as the central support reaction By, and then draw the primary structure, and further we will solve them using moment area method. Okay, so let's draw first your primary structure after removing this support at B. Okay, so now your structure is determinate, and it contains two loads. At the center of the span. Okay, so these loads are equal to 52 kilonewton each. Now what we will do, we will draw the bending moment diagram for this case. So since this is a symmetrical beam, okay, so your reactions will also be symmetric. That means your reaction in this case will come out as 50 kilonewton and 50 kilonewton at each support. Now let's draw M upon EI diagram for this case. So how it will look like? Since it is a concentrated force, so your bending moment diagram will be linear. Like this. Okay. I think by this time you know how to draw the bending moment diagram. And their maximum values are 300 upon EI, okay, so let me write it here. So this is your M upon EI diagram. Now what you have to do, you have to determine the vertical displacement at support B. So let me write here your vertical displacement at support B, that is your DL1. I think that is mentioned. Let me see that. If even if it is not mentioned, we are considering it to be DL1, and that will be equal to area of M upon EI diagram between A and B multiply by lever arm with respect to B, and in this case we are dividing it into one rectangle and one triangle. So let's see first for the triangle case. So that will become 1 by 2 For the triangle, the length is 6 into 300 upon EI, that is the maximum value of the triangle, and its corresponding lever arm will come out as 6 plus 6 by 3. Okay, now for the rectangle case, it will become 300 upon EI multiply by 6, and it will be equal to 6 upon 2, that will become lever arm. So your DL1 in this case will become 7200 upon EI plus 5400 upon EI, and that will become equal to 12,600 divided by EI, and that will become your displacement of the primary structure at support B. Fine. Okay. So now let's move to the next part of this question. So your next part is telling you that in order to solve the beam using unit load method, we need to solve for H1 in the equation. Equation is already where DL1 is the vertical deflection at joint B for the primary structure, and H1 is the redundant By. Now you have to calculate flexibility coefficient for the beam mentioned in the question number 7. So how we have seen in the in solving the flexibility coefficients, we have converted the beam to be a unit load diagram by removing all the external forces and providing a unit load at the center of the beam where redundant force is applied. Okay, so let's draw the diagram. So it will become a unit load applied at the center of the beam having a value of 1 unit. Okay, let's draw again the supports in this case. So in this case, A and C will be having hinge and the roller support respectively, and their corresponding reactions will be like this. Since this is a symmetric beam, so it will be having the reactions equal, and that will be equal to 0.5 units. Okay, so that will be equal to 0.5 and 0.5 respectively. Fine. Now what you will do, you will draw the M upon EI diagram for this case, and then we will see that using moment area method, what will be the deflection at B, and that will become your flexibility coefficient for this structure. Okay, let me copy this in the next page. Okay. Now, if we try to draw the diagram for this case, M upon EI diagram, how it will look like. Let's see that. So if we draw the M upon EI diagram, in this case, it will be a isosceles triangle, or you can say a linear diagram with maximum value at the center. So it will look like this. Okay. And its maximum value will come out as L upon, or sorry, it will be equal to 6 upon EI. Okay, so that is your M upon EI diagram. And its value is negative. Fine. Now, in order to determine the vertical displacement at P, how we will do using unit load method, or you can say moment area method. So using moment area method, let me write here my F11 will become area of bending moment diagram between A and B multiply by the corresponding lever arm with respect to B. Okay, so your F11 now will be equal to area of the bending moment diagram will be 1 by 2 into total length is 12 into 6 upon EI. Okay, now you have to multiply it with the corresponding lever arm, and that will be equal to 12 upon 3. Okay, if you solve that, you will get F11 to be equal to 144 upon EI. Okay, so now we have got the flexibility coefficient for the continuous beam that we are solving to be equal to 144 upon EI. Now let's continue for this question further. So in this question further, what is remaining? The unknown force, that is your redundant force By, which you are calling it to be X1. And how we will solve? We will use compatibility equation as mentioned in the question, and we will substitute all the corresponding values that we have calculated in the previous two questions, and substituting that, when we will simplify the equation, we will get the value of unknown. So using compatibility equation, which is DL1, which I mentioned previously, plus F11 into X1, which is your By in this question, will be equal to 0. Now, if you correspondingly substitute all the values that you have calculated, so your DL1, you have calculated it as 12600 divided by EI minus 144 upon EI into your H1, that will be equal to 0. And if you solve for H1, it will become 12600 upon EI multiply by EI divided by 144, and that will give you H1 to be equal to 12600 divided by 144, and it will be equal to 87.5. I will write it as kilonewton. Okay, fine. So this is how you will solve the problems for beams when they are statically indeterminate using force method. So now there is one more concept that is related to three moment theorem. Now I will directly use in this question. It is telling you that consider the beam given below. No external loads are applied over the beam, and in this case the support B sinks by 5 mm and support C sinks by 10 mm below the level of other supports. Okay, now we will apply the three moment theorem for the span ABC, and we have to write the corresponding equation involving MB and MC. Okay, so since internal supports will have some moments, but those which are at the end, or you can say end supports, will be having zero moments. That means your MA will become equal to 0. Correspondingly, also your MD here will become equal to 0. Now, using three moment theorem, I am not explaining in detail the three moment theorem. I am directly applying them and helping you in solving the question. If you need any help related to the three moment theorem, how it is derived, please see the videos for the week number 9 that is provided to you on NPTEL portal. Okay, so in this case, if you apply three moment theorem, that will become 4 times MA plus twice of MB multiply by the addition of the length for A and B divided by the corresponding moment of inertia, that is I, plus for the third case it is 3 upon I into MC, and that will be equal to 6E I upon 6E into delta upon L, and your delta in this case is 5 mm. So for the support beat is 5 mm, so I am converting into meter, that is 5 upon 1000, and the total length is 4 meter between A and B, plus corresponding support will also sink. So in this case it will be 5 minus 10, because 5 it is already synced. So 5 minus 10 divided by 1000 divided by the length, that is 3, okay, and that will give you 4 MA plus 14 MB plus 3 MC to be equal to 6 EI multiplied by 5 upon 4000 minus 5 upon 3000. As we have already mentioned, your MA is equal to 0. So that means your this part of the equation will be gone and your EI is 80,000. So let's substitute that. So it will give you 14 MB plus 3 MC to be equal to 80 into 6. That means 480 into 1000. Okay, multiply by the bracket value, that is minus 5 upon 12,000, and that will give you 14 MB plus thrice MC to be equal to minus 200. So this is what is asked to you in the question. Now, if we have to solve it further, like MB and MC and unknown, we will use this for the another span also, that is BC and D, BCD span. If we again apply this three moment theorem, from this again MD will get eliminated out, and you will be remaining with the equation having unknowns as MB and MC. Then afterwards, you will be having only two unknowns, that is MB and MC, and two equations. Okay, now you have two unknowns and two equations. Then you can able to solve the values for MB and MC. So we have one more method, that is three moment theorem, that will also can be utilized to determine for unknown redundant forces in the statically indeterminate beams. Okay, so this is what you have covered in week number 9. In week number 9, if I summarize, you have solved the problems related to beams when it is subjected to redundant forces, or you can say when the beam is statically indeterminate. We have solved the problems starting with when you have a free moment at the free end. Then we have utilized the same principle of force method. How we have done? We have first changed the redundant structure into a primary structure by removing the redundant forces, or you can say redundant reactions from the beam. Then we have solved the primary structure and we have got the deflection at the corresponding point. Then we have found out the flexibility coefficient. How we got the flexibility coefficient? We have applied a unit load wherein you can say when you apply the unit load at the redundant force, then whatever displacement you are observing at the corresponding point will become your flexibility coefficient. Then using the compatibility equation, we have determined the unknown force. So same thing we have then applied for a uniformly varying load cantilever beam, which is having a propped support at the end B. Then we have solved for the another question, which is having a continuous beam of 2 span subjected to a 50 kilonewton force at the center of each span. Again, we have solved that using force method. And finally, We have solved one question related to three moment theorem, wherein it is mentioned to you not to solve the question incomplete and thus just solve for the span A, B, and C. Okay. So I think whatever you have covered in this current week, you will be able to solve all the assignment problems related to that. So in case you have any problem, you can contact us. I am waiting for any queries if you have. Okay. After that, we will meet in the next session. Next session will be held in the next week. Okay. So I think we should wrap up this session as you have no queries for this. So let's wrap up this session. We will meet again next Saturday and we will solve the problems related to what you will cover in the week number 10. Till then, enjoy your weekend, complete your assignments, and have a nice day. Thank you, everyone. Have a nice day.